All right. So, data mining, right? That's what businesses do when they have these big piles of data and they try to find interesting patterns in the data, interesting and profitable patterns in the data. One of the original things that they used data mining for was just for those, by mail advertising, right? The flyers they send out to various people. So the question is, what should you put in a flyer? Given that the flyer costs like $1 to send, and you want to put in some products that people are likely to buy, you can customize that for a particular zip code. You can say, well, people in this zip code tend to buy this mix of products, so those are the things we'll put in the catalog, right? Other stuff, what else can you do with data mining? Well, obviously some other things. Anybody ever contribute to a charity through mail? And then you get a flood from a bunch of other charities? Anyone experience? Yes, I see some, yeah. So that's one of the things they do with data mining. Of course, they know a lot of people have overlapping interests. For example, if you're the sort of person that gives to Doctors Without Borders, you might also give to UNICEF, you might also give to Red Cross. They're sort of related, right? If you give to one sort of demographically affiliated charity, like one of the Catholic or Jewish ones, you contribute to one of those, you'll probably get a bunch of other ones. If you contribute something to poor kids in the Appalachians, you'll probably, get a flood of similar ones for poor kids all around America. Anyway, that's because these charities, they do data mining and they figure out, people who do this also do that, right? And they know, because it costs money to put those flyers in the mail, right? Last I looked into that, it was a few bucks for every mail item they send out. And so, yeah, they want to make sure that they're not just throwing money away. So they do data mining on stuff like that. Anyway, that's what data mining is. So finding new, often surprising patterns in data, could be positive correlations, things that happen together, could be negative correlations, things that tend to not happen together, and changing trends over time. Now, businesses always are looking at these patterns. They can identify the patterns. The math for that is pretty straightforward. But the question is, what can the business do with this information? So one of the classic ones that you hear about data mining is beer and diapers. When I first learned about this in a marketing class, anybody heard of this one, the beer and diapers bit? Beer and diapers? No, okay. Well, the story about beer and diapers is simply that you guys know Osco. I know you know Osco, right? Affiliated with Jewel Osco, they sell pills. Anyway, so Osco had a very large product line, what they call SKUs, SKUs, product codes. So they had a long list of SKUs that they were selling in their store, and they wanted to cut that down. They wanted to go from like 5,000 to like 1,500 different items because it was just a headache to manage that variety of items. But they wanted to reduce the items in a way that they didn't negatively impact sales too much, right? So they wanted to, number one, not get rid of popular items, but also not get rid of items that people kind of came in the store to buy. Even if they didn't sell a lot of them, it might be that Osco had these, products that were fairly unique that people came there to buy. And if they stopped selling them, then they'd lose those customers, right? Those guys would go somewhere else. So they're doing all this number crunching to look at what products they have and what they can safely get rid of without, again, negatively impacting sales too much. And one of the patterns they happen to observe is that there's a strong correlation between beer and diapers. And you might ask, well, why does that make sense? I mean, we all know why it makes sense, is that if you have little kids, you need to drink, right? But the thing that when they looked at the data, they're like, well, let's kind of come up with some story about this. And the story they came up with is that quite often it would be a late weeknight evening. The wife would say to the husband, hey, we need diapers for tomorrow. We're out of diapers. And the husband's like, we'll just use paper towels. And the wife's like, no, you got to go buy some diapers, damn it. The husband's like, fine, gets in the car, drives over to Osco. While he's there picking up diapers, he says, while I'm here, I guess I'll get some beer for myself. I've earned it. And so that was, the narrative they came out with. Now, you don't really want to sell beer and diapers together in the store, right? You don't really want to put a giant display of diapers right next to a giant display of beer with a big sign that says, you have kids, you need a beer, because there's obviously a lot of ethical concerns around that. But they did observe the pattern. There's just not a whole lot you can do with that pattern. Other things, sometimes things go horribly wrong. So this, the 1998 one, that's a, oh, that's a different one. We'll talk about the 12. I will talk about 12. You can look at the 1998 one. Let's see if Forbes. I'll bring up this one. Why can't I grab you? There we go. Look at this Forbes one. Diaper beer syndrome, right? Yeah. So you can look at this. Basically, it didn't work too well. All right. So here's one that they spent a huge amount of money on data mining generally. All right. So this one talks about the beer and diapers thing, but it talks more generally. You can spend a lot of money on data mining and not come up with any really useful patterns. And that kind of sucks, right? Then, yeah, you said, oh, yeah, we found all these correlations between products, but there's not really anything there you can go on to and try to make money at. So that's the horribly wrong there. Now, Target, this is another example of something that went horribly wrong in a different way. Not that they, wasted their time gathering data, but the story with this Target 2012 one, it used to be that if a woman got pregnant and she was expecting a baby, I don't know if any of you have been around a pregnancy before, but there's a whole lot of particular products that women start to buy when they are pregnant. And so Target, they did some number crunching and they looked at this stuff and they said, oh, we can recognize that when a woman is buying, this set of products repeatedly, we can assume that she's pregnant and we're going to send her a congratulations gift basket to get some customer loyalty. Because who wouldn't want that? Well, as it happened, there was some girl, I think she was like 16 or something. She got one of those congratulations gift baskets from Target. And her father was very upset, and he called up Target, and he had his little Karen moment, and he says, how dare you insinuate that my sweet little innocent daughter has done that thing that you're suggesting she did, And then a few months later, she had the baby. So, yeah, Target, since they've kind of backed off on that because, ideally we would live in a world where if you have a kid, it's a wonderful and joyous thing, and you're thrilled about it. But in the real world, not everybody's too thrilled to be pregnant at every time, and that's sad. But anyway, so yeah, Target, they kind of learned a lesson on that, and they backed off of this gift basket thing. All right, so that's some anecdotes about data mining, but we understand what data mining is. Let's move forward. Now, the field of data mining is a very big field. A lot of stuff piles into that. Number one, statistics. Data mining is very heavy on statistics. Number two, algorithm design. So not only is statistics involved, but you have to come up with a fairly systematic method for gathering, compiling, computing all these statistics, right? And the way that you're going to look at things, the prioritization that you're going to give to different items, how you decide a threshold of what's meaningful and what isn't, that all goes into the algorithm design. And of course, computer programming, right? Writing code that actually does all those things. So any of those aspects of data mining, yeah, you can make a living off of that. Now, of course, most business programs, including UICs, offer courses in data mining. We have a few. IDS 472, for example, is one. We have a couple of others that, depending on who you ask, they might consider it to be data mining, or they might consider it to be some other sort of analytics that, is not quite data mining. Anyway, I don't want to get into those semantic battles, but the point is, you take a data mining course here. What you'll probably do is either do some statistical analysis software, where you have a giant batch of data and you come up with some big regression model that describes, what variables are related with what other variables, or you'll have a big pool of data and you'll split it in various ways to same kind of groups. For example, well, we'll talk about some examples in the slides. So you'll do things like that. Like I said, a little bit of practice and a lot of theory about, why this stuff works. So, you only have in these courses, you get like, 15 weeks of lecture. So they're not going to teach you everything there is to know about data mining. You'll just kind of get your toes wet a little bit. Anyway, we're going to introduce a few of the major techniques: regression analysis, correlations, clustering, and trees. And you should know what all these are for the exam, be able to describe them, recognize examples thereof, that sort of thing. You won't have to do math though, because this is not a data mining course. All right. So the first one, regression analysis. If you've taken statistics, you've probably done some basic regression analysis. And the idea with that, a simple linear regression, you want to create a linear function, basically a line that predicts some variable. For example, something like if the temperature goes up, you're going to sell more lemonade at your lemonade stand, right? You could come up with some kind of function like that. Or if the temperature is cold, you're going to sell more coffee. If it's rainy, you're going to sell fewer hot dogs at the baseball game, things like that. So we're going to look at an example. You're an auto manufacturer and you want to produce some profit maximizing number of cars. And you've crunched a whole bunch of numbers and you've found that the variables that tend to be a good predictor for how many cars you're going to sell at that profit maximizing point. Number one, gas prices, right? As gas prices go up, people are going to favor smaller, cheaper cars, right? So there's a negative relationship there. As GDP growth goes up, basically, if the economy is doing well, people are going to say, hey, yeah, we can afford a car this year. Let's go buy one, right? So if the economy is doing well, you're going to sell more cars. Similarly, if consumer confidence is broadly up, because of course, GDP could go up, but it could be limited to a small subset of people, right? You could, for example, have a case where the people who already have a lot of money are doing very well, but the other, 90% of the economy is pretty flat. And you need a lot of those other people to be able to sell a lot of cars. So we also bring in consumer confidence, which is a broader measure where, you ask kind of like everybody in America, hey, what do you think about the state of things? And if consumer confidence is high, then that indicates that there's sort of a broad-based, trend towards buying cars. And last, interest rates. If interest rates go down, then it's cheaper in real terms to buy a car, right? So people are going to say, yeah, interest rates are good. This is a good time to buy a car. I'll do it. So those are the things they figure out. Now, after processing all of that, processing, I don't know why it says number, processing the numbers for several years, okay, you end up with a formula. So you have essentially a set of independent variables we'll call all of our x's, and they have some significant impact on the dependent variable y. So you essentially get this function that's in the estimate there, right? You're basically a standard line function, y equals a. If we had y equals a plus bx, then you'd be like, yeah, I've seen that before, right? But here we have a bunch of different x's. And any change in those x's, right, if we change x0 by 1, it's going to add b sub 0 to y. If we change x sub 1 by 1, it's going to add b sub 1 to y. So all of the, and so on. So any of those x's, they're all associated with what's called a beta value. The beta indicates how important that x is. Basically, if the beta is big for an x, then a small change in x is going to lead to a big change in y. If the beta is small, then a change in x is going to lead to a small change in y, right? The beta just shows how important the individual x variables are. And then we have an alpha, and alpha is the constant that just says, if all those x's are 0, then all those beta x products are also zeros. And then that equation just devolves into y equals alpha. So again, if all of those x's are 0, then we end up with y equals alpha. But again, this is the equation we have. And at this point, it becomes a plug and chug with our question, with our predictions for what the future is going to be. So for example, if we think, gas prices now, or for, that window in the future, if gas prices are going to be $3 a gallon, and we know that our beta is 30,000 because that was given to us by our, by our number crunching, then we would have, I'm just going to put this in. Let's do this. Let's do this in Notepad. And then we'll make it a little more real. All right. So y equals 500K plus what? 3 times 30K plus what? Domestic GDP growth. Here we have 3%, and that's a 15,000 beta. So 3 times 15K plus consumer confidence, 50 with a beta of 5,000. So 50 times 5K plus, actually that's a minus because that's negative, 5 times 25K. right? So y equals 500, actually that should be a plus. 500 plus 90 plus 45 plus 250 minus 125, y equals 590, 635, 885, 760. Right? I think if my math is correct, we would estimate based on this model that we're, our profit maximizing production quantity is 760,000. Okay, that's how that works. Basically, the steps for regression analysis, you do a bunch of number crunching to generate this model, right, with all the alpha and the betas, and then you just plug in your x values. Now, there is some weirdness with regression analysis. I'm just going to mention this. So what it is, you have a bunch of data, and you're going to try to get some line that stretches, from, we know that a line is infinite, right? It goes all the way from one end and all the way on the other. But one of the trappy things about regression analysis is it's really only valid for the range where you actually have data. So if you only have data for this stretch, then anything out, further out on this way is going to be pure conjecture if it actually fits your model, right? You won't really know. So you can say, yeah, our regression model is pretty good for this range, but if some of the values we're looking at are beyond that, then we don't really know. And what that means in practice for something like this, right? Suppose gas prices are crazy high, like for some reason they spike up to like $10 a gallon, and they've never been anything like that before. They've never been above $6 a gallon before. Then, the model may or may not give you correct results. It may say, it may be that this is so entirely different that it throws off all of our previous data, and our assumptions for reusing that data are no longer valid. I'm just mentioning that. That's kind of an advanced thing for people who may take regression analysis one day. That's fine. But what you should know, regression analysis, you do a bunch of number crunching, you come up with an equation, you plug values into the equation, and that's how you do your prediction of what the future is going to be, right? It's a kind of data mining. Okay. Second one, correlations. So suppose you're a retailer for video games, right? You're a GameStop or something, and you want to look into what video game products tend to be bought together. So you have as your relevant data the prior year's purchases of video game systems and accessories. So things like consoles, controllers, steering wheels, keyboards, games, whatever. And you do that, you present the data in batches of 1,000, right? So the number of people who bought per 1,000 transactions, right? So you have a bunch of correlation data, and the results in the chart are per 1,000 purchases, right? So for example, here we have consoles and controllers together. So for every 1,000 purchases that happened, 100 of them involved consoles and controllers, right? We're talking purchases that were of more than one thing. Obviously, consoles were always bought together with consoles. You can't really escape that. Controllers bought together with controllers. And you can look and see that some of these are pretty common combinations. For example, games, a lot of people, they're going to go into this store, they're going to go and buy a game and maybe something else, right? So that is a fairly common combination, is consoles together with games. For every, if there are 200 people, there are 250 people buying consoles, 200 of them are also buying games with it. And others are really rare, right? So keyboards, for example, for 250 people buying a console, you sold 10 keyboards. So that is an uncommon combination. It happens, but it's pretty rare. Okay, so what can we do with this? Well, there's three measures that you look for in this kind of correlation analysis. The first one is support. So support is simply the probability that two items are bought together, right? So for example, in our chart, probability of consoles and controllers bought together, 100 over 1,000, or 10%, right? So support indicates how popular is this combination. Second thing, confidence. Confidence is a conditional probability, right? So given, what is the probability that Y will be bought given that X was bought? So for example, the probability of buying a console then a controller, right? So given that someone has bought a console, what's the probability that they also buy a controller? Is 100 out of 250, or 40%, right? So we look at this. Here, of all the people who bought consoles, 100 of them bought controllers. So controller and console by itself is only a 10%, probability event, right? 100 out of 1,000. But if you already know that somebody bought a console, then they're actually much more likely to buy a controller, more likely than average. Okay, the average number of people who bought controllers, 300 per 1,000, so 30%. So you're actually a bit more likely to buy a controller if you're buying a console that same day. And then the last one is lift. Lift is the increased probability of buying some product given that X was bought. So in this case, like we said, the probability that somebody buys a controller after buying a console is 40%, but the base probability of buying a controller is just 30%, right? So there's lift. Somebody is more likely to buy a controller if they bought a console at the same time. And so we can say, how much of a lift is there? Well, in this case, it's about 33%, right? So we do the math, we come up 40% divided by 30%, 1.333, so about a 33% increase. Now, so that's what those definitions are, but what can we do with them? Well, if you find a pair of items that have high support, that's going to be a popular combination. It's good for promotions. It's what people are coming into your store to buy, right? You can also do that to streamline your operations because you say, hey, here are some things that people very often buy together. That's the root of things like McDonald's Happy Meals, right? So the Happy Meals were introduced in the 70s. And the reason why is because McDonald's observed that a lot of families were coming in and they were buying the same orders for their kids, right? They would say, well, give me a hamburger and a small drink and a small fries, and that's what the kid will have. So McDonald's said, you know what? So many people are coming in and buying this. Let's just make it a combo, right? And then people will know exactly what they're getting. And if nothing else, it streamlines the process of actually placing those orders. Other things, high confidence, right? So remember, confidence is a conditional probability. People who bought this also bought that. So one thing you can do is you train your employees to recommend add-ons. So what's a typical add-on you might hear at McDonald's? Like if you go through and you place your order, they don't do it as much as they used to. Yeah, but what do they ask after you ask your food? I'll be like, I'll have 2 burgers and a large fry and then 2 more burgers and a Diet Coke because I'm watching my weight, right? And then what do they ask if you want? Apple pie, that's the classic one, yeah. Would you like to try an apple pie with that? You're like, no thanks, right? But yeah, many years ago, I had a friend who every time at the end of the order, they'd offer him something and he'd say yes. So he'd be like, okay, your total is $12.66. Would you like an apple pie with that? Yeah, okay. All right, your new total is $14.03. Would you like to try a coffee with that? Yeah, okay. Your new total is $6. They went like 8 times until finally he's like, your total is $30. Just get your food. Yeah. Anyway, I don't know. That was kind of funny. He broke McDonald's. Anyway, excuse me. So you can train employees to offer add-ons, right? If there's a lot of people, especially if you're buying Happy Meals, and you're like, the kids want the cookies or the apple pie or an ice cream or something, right? Or whatever the promotion of the week is. If it's summer, they'll offer you slushies or something. Those are the kind of add-ons, right? Also, coordinating product placements in stores, right? If you know that there are things that people buy together, one possibility is you put them together physically in the store so they're easy to find, right? If you know that somebody's going to buy a console and a controller together, put them next to each other so they're right there, right? Or you could take, kind of the asshole store design approach. You could put them at opposite ends of the store, forcing people to wander through and see everything. You could do that too. Stores do that. Anyway, last one, high lift. So high lift is differentiating between broad and narrow popularity. So for example, suppose 80% of McDonald's customers buy fries, right? Anytime you go to McDonald's and you order something, 80% of those people buy fries. In that case, a confidence of 80%, somebody who bought this has an 80% chance of buying fries. It sounds high, but it's not actually high relative to the baseline, right? The baseline probability of buying fries is 80%. So you'd have to be like, 90% to, be noticeable. Same thing, we can see this in our chart here. For games, down at the bottom right-hand corner, 80% of these purchases involve games. So when we look at our number for consoles and we see, yeah, for consoles, 200 out of 250 people, also bought games when they bought a console, that's 80%. So the confidence is 80%, which sounds high, but the lift is actually 1, right? There is no lift in sense. We're saying that the fact that somebody bought a console doesn't mean that a customer is any more likely to actually buy a game. So there's that. Anyway, so that's what you can do with that stuff. So support, again, you identify your popular products, you can promote them, you can say, hey, if I'm going to run some commercial, you might as well display the products that the combinations that people are coming into your store to buy, right? And again, you can streamline operations. If you have high confidence, you can cross-train employees. You can, if you know that people are buying both consoles and controllers together, you could train your employees to be reasonably knowledgeable about both. So that if somebody's buying a console, they can suggest a controller, and in particular, which controllers are pretty good in terms of what somebody's looking for. And lift, again, helps you distinguish between confidence that is meaningful and confidence that is not especially meaningful, right? It's a way of measuring that. Okay. Now, these next two, we have clustering and trees, and they're pretty similar, but there is a difference. All right, so we'll start with clustering. So suppose your problem that you want to use data mining for, you have a scholarship program, right? You're some university, you're running this scholarship program, and you want to grant those awards only to students that are actually pretty likely to graduate, right? You don't want to give this scholarship to somebody who's likely to drop out in the first year. So you crunch a bunch of numbers and you find some important correlations that here are the attributes of people that are likely to stick it out and graduate. Number one, their high school GPA, right? Students with good grades are more likely to stick around through the end of college. High school attendance, right? Attendance is positively correlated with doing well in school. That's not a big surprise. And you might also find extracurriculars are important for whatever reason, right? You've crunched the numbers and you have remained agnostic about really the story about why any of these are meaningful. You've just observed that they are meaningful. So use that as the basis for your scholarship program because you want to give it to people who are likely to stick it out. Now, what you then do, I'm going to pull this into Paint, screen. And you have your 3 axes, right? So however you're going to do them, we can do it like, whoop. All right, so this one, we can say this is GPA. This one is extracurriculars, extra C. And this one, what is attendance, right? And if these are all good, right, as in, kind of out towards this corner, the upper right corner of the cube, then we say, yeah, this is, these are students that are probably going to do well. So what you would do in clustering is you would try to develop some sort of function that if you're on the right side of it, you're looking good, and if you're on the other side of it, you're not looking so good. So maybe something like this, right? You would say that in this function, high values and high probability of graduation, right? If you're on that side. Oh, yeah. Okay, over here, low values and low probability of graduation. Okay, and the blue dots, we'll say blue dots success. Let's graduate, and then no success, not success. Okay, so I'm going to fill in those circles. What are you doing? This is a lot harder than it looks. Okay, so you get the idea, I hope, anyway. So the point is, with this kind of analysis, what we're doing is we're taking our data space and we're trying to divide it into sections. And we're trying to say, this section, the data points on this side are like each other. The data points on this other side are like each other, right? But you're basically coming up with two clusters in this case of just saying, yep, it's like this on this side, it's this other type on the other side, okay? That's cluster analysis. And again, I'm just showing you a simple way to do it with a picture, which is something that humans are pretty good at. But if you have a whole lot of data points, obviously, you're going to use some kind of number crunching software to do this work for you, right? And you'll come up with some function that says, you know, if you're on this side of the line, or in this case 3D, if you're on this side of that plane, then you're data type 1. If you're on the other side, you're data type 2. And you could have more than 2 data types as well. Okay, so that's clustering. Now, the next one, trees. Trees are similar but different. Trees, basically, you're sequentially applying rules. You still have some data space that you're dividing, so it's like clustering that way. But a clustering, you just do a simple split into groups. With tree analysis, basically, you can have groups and subgroups and subgroups and sub-subgroups and so on, you know, as long as you're finding differences between them. So trees are basically a sequential process of potentially creating many clusters. So here's our problem for this one, for tree analysis. A bank wants to minimize its risk of loan defaults by filtering out risky loan applicants, right? It only wants to lend money to people that it considers to be, you know, reasonably good risks. I mean, anybody could potentially default on a loan, but the bank wants to pick low probability ones. And they've crunched a bunch of numbers, and they've come up with some relevant variables. They found that in various ways, income, debt to income ratio, work history, and age of the loan recipient, all of those factors are somehow relevant into whether someone's a good or bad loan risk. Now, when they've done their tree analysis, the first thing they do is split the data on relevant variables. So they might, for example, find that a group with income above 75K per year is a pretty good risk overall. And a group with income below 75K is not such a good risk, right? But of course, there's going to be subgroups within the higher income group that are going to be high risk, you know, and there's going to be subgroups within the lower income group that are going to be low risk, right? So what do? Well, you break it down a little more, and they may find, we'll say for purposes of this discussion, this is what they found. Even if you have high income, if you have a high debt to income ratio, you're not a great loan risk, right? So we'll exclude mortgages from that. But for example, if you're carrying a lot of credit card debt, they might look at you and say, yeah, you're making money, but you're spending it faster than you make it. I don't know if we're going to be, you know, loaning this out to you. But if they have a low debt to income ratio, they pay their credit card bill every month, then you'd be like, yeah, they're probably good for it, right? Likewise, for the lower income group, they might find people who have at least 10 years of work history, right? They're not making tons of money, but they're responsible, they've got a job, they show up every day, they do it, you know? They're probably the sort of people that will pay back the money, even though, you know, they don't have a huge income. Well, they'll still probably pay it back. On the other hand, you might identify that a group that has less than 10 years work history, not such a good risk, right? If somebody's like 50 years old and, you know, they've been out theoretically in the workforce for 30 years, but they've only actually worked less than 10 years, you might look at that person and say, yeah, you kind of don't have your life all together. You know, I don't know what you've been doing, but it hasn't been going to work every day. And, you know, maybe there's a lot of bad stuff in their, you know, their history that's affiliated with that. But even with that group that has less than 10 years of work history, you might identify some issues. For example, you might say, well, if somebody is younger than 28, maybe they don't have time to build up that much of a work history, right? Maybe they've been in school, they've been in college. You know, it might actually be that these people who are young, they don't have a lot of money because they're in college, right? And they don't have that much work history because they've been in college. But you might still identify that, yeah, overall, those people are a pretty good risk, right? The ones to worry about are the people who reach middle age and have never figured out how to make much money or keep a job for very long. Those people, yeah, they're probably not a great loan risk, okay? And anyway, this is all hypothetical. I'm just saying this might be what the bank crunches the numbers and finds, right? So if you do it like this tree analysis is basically a sequence of clusters, right? So something like this, here's your whole big pile of data. And you might first split it into what? High income or low income, right? I know that I don't want to say that 75K is low income, but I'm just saying for purposes. And you might just looking at it, you might come out with something like this. But you're like, you know what? If we look at this with a little more detail, this is what cluster analysis would be. Well, with tree analysis, you look at it with a little more detail and you say something like, okay, high income, let's break that down a little bit. And you can break it down into different variables. You might say, you know, you might say low debt is a good risk, like in our example, and high debt is a bad risk, right? Likewise, for low income people, you can split that. You can say something like, what do we have for low income people? Work history, right? We'll fill that in. So we'll say limited work history, and here we'll say solid work history, right? You might find those are different groups. So again, with cluster analysis, you keep the data in one shape. You know, you look at it, you split it with one simple rule. With tree analysis, it's kind of the same thing. You're doing cluster analysis with cluster analyses within cluster analyses, right? And even for limited work history, right? This one you could potentially split down even further. You could say something like, right? So limited work history plus older, but if we look at this one and we say, you know, limited work history, but younger, right? It's a good risk. So this is the sort of thing, right? So tree analysis, again, similar to cluster analysis, but the big difference is it's sequential. You're sequentially applying these rules to split the data into same kind of groups. Okay, that's the difference. Now, it is traditional that we talk a little bit about ethics. So in the wake of Enron, if you don't know what Enron is, you should probably look that up because all of your professors throughout your whole degree path will probably mention Enron at some point. Enron was a company that famously crashed and burned about 20 years ago after a long series of ethically questionable business decisions. And part of the analysis of that, the academic community kind of looked at itself, looked in the mirror and said, we have been really irresponsible in pushing the anything to make a buck kind of trend. And we can do better than that. So one of the things they did is they said every course should have some ethics component to it, right? At least a mention or a consideration of ethics to let people know that, yeah, their business is good and making money is good. That's what we're trying to do. But there's more to life than, just stomping over other people to make a buck. So this is where I bring it in, is in talking about data mining. So of course, when you build a model, you might have machines that implement the model, that do the math, but it's humans that build the model. It's humans who decide what variables are going in, importantly, what variables aren't going in, how important different variables are, and the historical window you're looking at, right? So if you look 20 years back in data, you will probably get a different model than if you only look 3 years back in data, right? And it's not the sort of question that you can easily say one is better or not better. And you might simply ask, is it enough that predictions are accurate? So one problem with just, applying a model and treating that model as the final truth is that there's always going to be some exceptions. Okay, so let's take a minute. So suppose you have this scholarship one. This is something that's probably relevant to many of you. What are some reasons why a person might have not a great GPA, but might actually be a good candidate for a scholarship? Basically, what are some individual situations that might explain a GPA that's maybe not the highest? What's that? You think they did a lot of extracurriculars? It's possible. It's possible. I'm saying, I mean, what, for example, suppose somebody is a very smart student, but they're ESL. Everybody knows what ESL is? What's ESL? English as a second, thank you. English as a second language, right? It might be that, yeah, you know what? You came to the country at 15 and you transferred into high school because your parents moved over here. And yeah, you knew enough English to get by, but you just moved here from overseas where you weren't speaking English before, right? That's something. That's defensible. You might look at that and say, yeah, well, you know, he didn't even speak English when he got here and he graduated with a B average. That's probably pretty good. Okay? And you can think of some other ones. I didn't want to go in and say that, yeah, maybe your GPA isn't that high because a couple of your teachers were real dicks and they hated you and they just marked you down for no reason. Yeah, I mean, conflicts happen, although that would not tend to bring your GPA down too much. It might bring it down like 1/10 of a point or something. What else? High school attendance. What are some reasons that somebody might have missed a lot of school, but you would not think that it might affect them in the future, right? They would still be reasonably likely to graduate. Why might somebody miss a lot of school for a reason other than just being irresponsible and skipping school? Sure, family problems, right? Maybe you got a sick grandparent you got to take care of, right? Maybe your parents is an alcoholic and their life is all screwed up, right? And you got to kind of help them out with that, which isn't right, but it does happen. Maybe you got cancer, right? Maybe you got cancer as a teenager and you drop out for like 3 months, 6 months, whatever, right? Shit like that happens. Sure. What else? Extracurriculars. So it's nice to see people that are doing sports or chess club or whatever, but what's something that might not show up in extracurriculars, but it's actually maybe much cooler from terms of like a scholarship board looking at? What's something that's better than football or chess? Sure, that might be good, right? You do a lot of charity work, but it doesn't show up on extracurriculars, right? That's good. What else? I mean, maybe you're a teenager who's actually running a business, right? Maybe you have some kind of small business that you do. That's cool. Maybe you're a streamer, right? Maybe you're making $10,000 a year doing YouTube videos, right? Maybe what? Maybe you're actually involved in some sort of little research group. There are on occasion high school students that get affiliated, you know, with research even here at UIC, right? I mean, you kind of have to have connections to do that. You gotta, maybe your parent is a researcher, or, you know, you're buddies with a high school teacher who happens to know somebody who does research, but it does happen. And it does happen that occasionally high school students do really cool stuff that you look at that and you say, wow, that's way better than football or chess club, okay? So what I'm saying, it's nice if your model gives you good results, right? In the sense that people are just going to look and say, yep, you know what? The average rate for graduation is 50%. Our model's doing a pretty good job. We're getting like 80% graduation using this model, but you only get to run the model once, right? So you might consider in evaluating that, hey, what would have happened if we had done this other model, for example, and given it to some of these other students? I don't know, maybe you would have done better. All right, so my point is, you know, data mining is a good thing. It is a powerful tool, but it is certainly not the only path to truth, and any model is inevitably going to leave out some important factors, or at least some factors that are important for some data points. All right, because if you look at this chart, right, what we're doing fundamentally is this. When we draw this chart and we do this split down the cluster, there's a couple of blue data points on the left side of the line, right? Those are people that were successes, even though the model said, yeah, probably not. And you look over on this side, there's some red data points over here, right? There's some people that you thought, yeah, I thought it was all going to work out for them, but it didn't, right? Yeah. Anyway, that's all. That's all I'm saying. All right. Now, we got to make a dent in this other lecture, so I'm going to go ahead and move on to that. And cloud services. Excuse me. Okay, we don't have to make a huge dent in this. Okay, so we're going to cover basically the start of this lecture. So Amazon Web Services and why businesses needed the cloud. So in case you didn't know, Amazon has the largest cloud operation in the world. So this is, chart cloud infrastructure market size, pretty recent. Total worldwide, whatever, is about 200 billion. Amazon has about 34%, so pretty close to 70 billion, right? And you look at that, Amazon is bigger than, about as big actually as the next three put together. So Azure, Google, and Alibaba together, about 36% versus Amazon's 34%. So annual cloud service revenues for Amazon, about 70 billion, has 34% market share. That's been pretty constant the last 5 years or so. But the revenues themselves, they're way up. Used to be only 25 billion in 2018. So that, you can do the math. That was growing really fast and still is. The next biggest three in that chart have about 36% market share. If you look at the next biggest 10, it's about 20% total. So yeah, Amazon is very, very big, but Microsoft in particular is making a serious challenge against them. And Google, to an extent, is making a serious challenge. But yeah. Now, if you want to learn more about Amazon's cloud services, AWS, Amazon Web Services, that's kind of their umbrella for all the cloud services they offer. You can go there, browse around, read a little bit. But interesting thing, Amazon was almost accidentally fell cloud, right? So when Amazon was 1994, cloud didn't really exist. There wasn't any place where a business could go if they didn't want to do the computer stuff themselves. There wasn't a place where businesses could go and say, yep, you handle all my IT stuff for me. It just didn't exist. Businesses maintained their own data, which they needed to maintain, right, for a variety of reasons. But the big one is just, it's their data, it's their customers' data. They need to keep that private and secure. You can't just go give that to anybody else in the world. So, but the way it happened for Amazon, right, circa 2000, Amazon was building lots of tools to help retailers sell through Amazon, right? So Amazon had this nice platform, they were selling a bunch of stuff, and they started letting outside vendors sell through Amazon. Well, Amazon's engineers, it was getting to be a big headache. They were having to design a lot of custom interfaces. Every vendor that was selling through Amazon wanted something kind of new and different. And Amazon's people were saying, yeah, we can design we can design an interface that has that. But it gets to be a big hassle, right? If you have a lot of different interfaces and a lot of vendors clamoring for more detail, eventually, right, it's just too much work. And so Amazon said, yeah, you know what? People can use standard interfaces. So Amazon started to realize that not only was this a headache, but there were various ways they could reuse application components, right? They wanted to, number one, use a standard interface, but all the application components in there, things like shopping carts, objects for sending transaction information throughout the system, notifications for reordering, all those you can design as standard application modules. And if you've designed an interface that is already standardized, then it's very easy to design those additional standardized modules to fit that interface. So eventually, there was so much standardization built in, it became the foundation of Amazon's cloud. So let's talk about a simple way that this might happen, right? So suppose, screen, right? Suppose you have two vendors selling different products through Amazon, okay? What's going to be the same on their web page? What's going to be the same on their product web pages, right? Well, things like a description block, right? The set of images and their locations, right? The interface with the recommender system, right? So we know how the page is going to look, right? Up at the top, there's going to be an image of the picture itself. There's going to be a title on it. There's going to be a text blurb that describes what it's about. Standard set of item details. So for example, if it's a book, it'll have stuff like publisher, author, date, condition, number of pages, etc., right? All those kind of standard fields. So you built up this, you know, basically some sort of XML or JSON structure that you can, all these vendors can use. And once you've designed it for use of two vendors, right? If two vendors are using the same template or interface for their pages, you can easily bring in new vendors to sell the same product with basically the same structure. Okay, so if you have two guys selling books and they're using the same interface, you've established multiple vendors can use this interface, right? It has all the stuff that vendors are going to need. So you say, hey, you know what? If you're selling a book on Amazon, use this standard format. And the vendors will be like, yeah, okay, we can do that. And then you don't have to design custom interfaces, okay? If you convert that set of fields, right, as a list to a generic blob of data, then at that point, you pretty much have cloud, right? You are handling arbitrary lumps of data, and you know the structure is flexible. So you can handle any data for anybody at that point, right? So you say, okay, we start off with these kind of standard interfaces. It's nice that every vendor can use these standard interfaces. That's better than designing a custom web page for everybody. But if you come up with some translator, if you have like an XML list of fields and you use that to build the web page, then suddenly it's a lot better, right? Then you can take any kind of data. It doesn't just have to be for books. You can have a flexible structure that accommodates books or DVDs or clothes or crocodile xylophones, whatever, right? Music, you can do anything. And that's, you know, essentially the foundation of cloud, is that anybody can show up, upload whatever kind of data they want, retrieve any of their data they want. You don't care what data people are storing there. You just make it available for them to, you know, save and retrieve their data. Okay, I hope that made sense. All right. There's a couple popular tools on Amazon. Amazon has a lot of cloud service that they offer, but the two I'm going to mention, number one, simple storage, or S3. So S3 is a massive key value object storage system. Remember what a key value store is. We talked about that. It's essentially a large blob of data, can be any format that the client wants. And the key just is a unique identifier. So basically, Amazon has this long list of blobs of data, and the blobs can be huge. They could be up to 5 terabytes of data, right? So actually probably stored on a large blob would be stored on multiple pieces of hardware. Amazon simple storage system, last I checked, estimated to hold 5 trillion objects. Most of them are smaller than 5 terabytes, but you know, 5 terabytes was the cap. Anyway, so what this makes sense for, imagine if you're a business and you have a lot of data and you want to on Amazon, right? You don't want to deal with it in your own systems. You don't want to have to build a system to store it and make it fast to retrieve the data and deal with upgrades of hardware and stuff. You say, you know what? Amazon does a good job. Yeah, they're going to charge us to do this, but that's all right. It's money well spent. We'd have to pay it if we did it ourselves too. So key features, it's cheap, it's reliable, it's accessible. Businesses like that. The real difficulty was analysis. So imagine if a business has a huge pile of several terabytes of data under their own roof, right? They can build some system to do some number crunching on that, right? Basically to do analytics, data mining, whatever. They can implement that kind of system. They don't really want to build that system though, right? Most businesses don't want to custom design their own analytics, right? They're not in the analytics business. They're in the business of making shoes or selling books or making cars, whatever, right? They don't want to do analytics. But when Amazon said, you know what, not only will we store these large blobs of data for you, we will also give you the ability to run detailed, complicated queries on this data and they'll run faster under our roof than they would ever run under yours. Businesses are like, yup, sign me up for that. Okay, so that's what simple storage is. Businesses can store their data and run analytics on it, and that's the real selling point. Because if businesses couldn't run analytics on it, yeah, they'd probably keep it under their own roof, right? Storage isn't that expensive. It's the ability to do analytics that really makes this a useful product. The other one, Amazon's Elastic Cloud, or EC2. That's the core of what's called Amazon's cloud computing service, right? So simple storage is basically storage and analytics. It's still in the cloud, but Elastic Cloud is essentially when you're running applications in the cloud. So for example, if you want to do your transaction processing through Amazon, right, you set up some web front through Amazon, and then you handle your transactions through there. Or if you have a lot of analytics you want to run or other applications you want to host, you can do that through Amazon too. So what users do for that, they rent what are called virtual servers. So it's not an actual physical server machine, it's slivers of capabilities from many machines that together is the equivalent of a server, right? So Amazon has tens of thousands of servers. In most cases, they're not going to rent specific pieces of hardware to outside users. They're going to run your applications on whatever machines it makes sense to run them on at that point. So you get a lot of slices of servers. And the slices are called elastic compute units, right? So basically Amazon sells server equivalents. Anyway, so what people do with EC2, again, you can deploy applications like analytics software, transaction processing software, and of course, there's backup capability built in. One of the key reasons why businesses put applications in the cloud is because they have busy times, right? And the difficulty businesses always had was if you have a busy time during the day, you have to have enough hardware and system capacity to handle that busy time. But because it's a fairly short busy time, most of the rest of the day, that equipment is going to be idle. So a lot of times you're paying a lot of money for equipment that's gathering dust. So with something like this, you can pay for what you need when you need it. And even though Amazon is making money on it, it is still a better proposition for most of these businesses. Okay. What time do we have here? 10:34. All right, I'll talk a little more. Like maybe 3 more slides. Okay. So we did an image before of cloud instance. So a cloud instance is basically a gigantic cluster of servers, right? A whole bunch of servers that are designed to simultaneously support a bunch of different users, maybe run different operating systems, run a whole bunch of different applications on different machines. Essentially, it's like a utility company for all these computing tasks, right? Application hosting, data storage, computing power, right? Number crunching internally, that sort of thing. So just like a utility where, there's an outlet on the wall somewhere, there is, and you plug your device into it and magically electricity comes out because you've paid your electric bill. Same thing with the cloud. You hook up your network connection to somewhere, and because you've paid the ISP, you get, and the cloud service, you have access to that functionality. So users connect to clouds via some website. The cloud system seamlessly directs users to whatever server has their applications and data, right? You go through some interface. Amazon knows what machine a given user's data is on or where their applications are, and they will connect the user to that particular machine when they go to the interface, when they go to the web. And of course, they provide automated backup and recovery services. So, your data automatically gets backed up. If an application fails, Amazon will bring up another server running that same application and make your data available to it. So that's essentially what cloud does. So from the outside, it feels like you're just connecting to some server directly, but in fact, there are many users connecting to many different pieces of hardware, and they don't have to worry about what particular piece of hardware they're connecting to. Same thing as when you put your plug into the outlet, right? You don't need to know what particular generator in the grid is bringing the electricity to you. Doesn't matter, right? What matters is that you get electricity. All right. So a couple slides before we, this would be a good place to end it. So once upon a time, before about 2010, most organizations handled their own data. They had all their own servers, they did all their own storage. And the reasons for this, well, number one, biggest reason always, it was business as usual, right? This is the way people did it. This is the way everybody did it. There was no competitive pressure really pushing businesses to do something different. You know, if you're inside the business and you're lobbying for a shift to cloud, well, that's a big risk you're taking on, right? If it goes great, yeah, people will pat you on the back and say, oh, nice job, good decision. But the credit for that is going to be taken by people elsewhere in the organization. Whereas if it fails, right, it's going to go on you. So the old saying, success has many parents, but failure is an orphan. Yeah, this is a big part of why nobody really wanted to push for this until it became clear that it was needed and other businesses were doing it. Number two, security perceptions. So there's definitely a security concern if you take data that you have and you give it to someone else, right? You have to be really sure that they're going to do a better job with security than you will. Because otherwise, again, if you're the guy that pushed to send this stuff to the cloud and then there's some security breach and all that data comes out, right? And yeah, it's going to look really bad for you. And in fact, in the early days of cloud, this was a pretty legitimate concern, right? Because these cloud services mostly didn't have they couldn't have a long history of doing cloud stuff. So it was kind of taking a big leap into the dark. Number three, control over system design. There's a lot of issues. If you've designed a system under your own roof, you know what parts of the application are running on what pieces of hardware, you know how its performance is going to be, you can tweak it if something goes wrong. Once you send it to the cloud is going to deploy those application components wherever it sees fit, and maybe it'll work well, but maybe not. And in fact, you had a lot of businesses that they had a system that worked reasonably well under their own roof, but once it went to the cloud and application components were no longer on the same piece of hardware, it started working a lot worse. So, for example, one of the things we've talked about with relational databases is they can work pretty well as long as the amount of data is not too big and you can keep it all on one piece of hardware, especially in RAM on that one piece of hardware, right? Because RAM is super fast. But imagine if you deploy your stuff to the cloud and the cloud says, you know, this data that we used to all have on one machine, because it was under our roof when we designed the system that way, when it got deployed to the cloud, those pieces of data ended up on separate machines. And so what used to all process in RAM, you know, super fast because it was on the same machine, once it went to the cloud, maybe it wasn't processed in RAM. Maybe there was a lot of network communication that has to happen. And even though these cloud networks are fast, they're nothing like as fast as RAM. You're never going to have data going over a network as fast as, you know, if it's already there running in RAM. So yeah, you would often see that kind of problem where the cloud would split up some operation that used to be on the same piece of hardware, and then it didn't work so well anymore, right? Other things, you might just have data growth. As you deploy something to the cloud, maybe it was fine under your roof because the amount of data was relatively small, but once you send it to the cloud, you start piling up lots and lots of data. There's so much data, eventually it spills over across multiple machines. And again, what used to be fast because it was all on one machine, suddenly no longer very fast because it's broken up across multiple machines. Anyway, and last, accessibility. If you've ever tried to download, you know, a gigabyte of data from the cloud, imagine trying to download a terabyte of data, right? So a gigabyte, it'd take a while, right? Maybe take like a minute or so to download a gig. But imagine if you have 5 terabytes of data up to the cloud and you want to download it all so that you can run some number crunching on it under your own roof. That's going to take a really long time. I'm going to do a little math here. Oh, wow, we're running. Okay, good. Well, maybe this will be it then. I'll just do this. So back in circa 2000, if you had a great connection like a T1 line, T1 was like top of the line back then, you might get an incredible 1 megabit per second download speed. And that was super fast. That was like blindingly fast in 2000. That was like, oh man, how are you getting that much, right? But basically that means 1 megabyte, 8 seconds. So if you had 1 terabyte of data And a large business could very easily have a terabyte of data, and you wanted to get it all. How long would that take? Well, 1 terabyte equals 1,000 gigabytes. 1,000 gigabytes equals 1 billion megabytes. So how long will that take? 8 billion seconds. Oh no, 1 megabit. So 8 million seconds, right? Because you get one, yeah. No, I'm right. 1 million megabytes. That's huge. Sorry, I can't do the math. 1 equals 1 million. I knew there was something off there. The numbers were too big. So it would take 8 million seconds to download on that one line. Okay, how long is 8 million seconds? Well, 80,000 seconds is about 1 day. So 8 million is about 100 days. It would take a really long time to download all this stuff from the cloud. Now you might say, yeah, I'll set up some parallel system where I'm downloading chunks on different streams. Sure, right? You're not going to tolerate that it takes 100 days to download this. What I'm saying though, it would take a really long time, 20 years ago, to download a lump of data that big, right? No matter how you slice it, it's going to be not as fast as you want. Whereas if you have all the data under your own roof, it's already stored in one system. You don't have to deal with that kind of download speed. So this was one of the big issues for cloud. How do you get the data, right? If it's all stored up there, right? Amazon's S3, yeah, you can run analytics on that. But if you just wanted to download all your data so you could do some stuff under your own roof, it's prohibitively slow, right? This is not what you want. Anyway, we'll come back. We'll come back on Thursday, wrap this up. It'll be good times. All right. We'll see you next time.